Hello everybody and welcome to the CATIA community and today's webinar on sustainable high-performance thermal systems design and simulation. If you have any problems during this session, please let me know through the chat window. If you have any questions for our presenters today, please ask them through the chat window during the session and we'll answer them at the end. This webinar will demonstrate the value of applying multidisciplinary approach using the 3D Experience platform and multiple brands, in particular CATIA and Simulia. We are joined today by multiple presenters. From Dassault Systèmes, I'd like to welcome Ed Tate, Victor Marie Leburn, Satish Candice May, Chim-Wei Chang, and our partners Alessandro Prochelli from Claytex and Manuel Grabir from TLK Energy. I am now going to hand over to Satish, who will start today's proceedings.
Thank you, Jessica. Sustainable high-performance thermal system design and simulation. What is it? We all know the vehicles generate heat, and thermal issue is not just a performance issue. It's a critical safety issue. So the vehicle manufacturers, they care a lot about how they can manage this heat. And we are going to talk about this for the next hour. So what we do is, with this offering, we help companies to design and manage their thermal system. There are various ways to design a thermal system. You can design a thermal system in an isolated test rig and then put them together in a vehicle. Vehicle is a collection of multiple systems and subsystems. So what happens when you put together these subsystems in a vehicle, the performance changes. And most of the time you get into trouble if you don't have an integrated solution, integrated evaluation. So how can we design in a competitive manner so that the vehicle development cycles are not impacted? So that's what we are going to talk about today. So with our offering, the mechanical and thermal engineers and designers then collaborate and do a multidisciplinary evaluation and partnership in a virtual environment. So what does it offer? It enhances performance and optimization of thermal and thermodynamic systems in a real operating condition, and it significantly reduces development time and cost. We all know that compared to several years ago, maybe 5-10 years ago, vehicle development cycles have shrunk significantly. There's a significant rush to get into market sooner than later. So these are critical metrics the vehicle manufacturers care about. And also due to the shrunk development cycles, and also creating a physical prototype can also impact the development cycle adversely. So all these can be addressed by adapting a digital solution. So by designing a vehicle on 3D Experience platform, you can have the best of CATIA and Simulia and realize a vehicle that is optimized for performance, cost, and efficiency. So what are the values we provide with this offering? We can improve efficiency by managing thermal energy efficiently, protect thermally sensitive components and sensors, and reduce time to market, and increase product quality, and reduce physical testing. By increasing this product quality and addressing thermal issues, we can also significantly reduce the warranty costs and protect the brand image. And why is it important? If you look at a vehicle, everything that moves or does a calculation, something like a sensor, it generates heat. The magnitude varies. And we need a solution that can cover a sensor and an engine. These are quite different in sizes, and the amount of heat generated is also quite different. And traditionally, vehicle manufacturers have relied on testing methods. And the downside of that is creating the prototype takes time. And also there's only a limited things you can do with a hardware. And heat, you cannot see heat moving. And in a simulation, you can see that and see what are the causes and see the effects. There are a large number of ways to design system, but finding a method that has a competitive advantage is crucial to be at the cutting edge. By using 3D Experience platform, we offer a solution that connects modeling and simulation. Basically, it's CATIA and Simulia to realize optimized performance across multiple engineering disciplines and reduce physical prototypes and do the design right the first time. Ensure quality with an efficient, modular, robust solution. How do we deliver? We have a model-based workflow on the 3D Experience platform, provides seamless collaboration between various engineering disciplines and designers. And simulation activities are now tightly integrated with the design. So most of the time, when a vehicle is released and during the development cycle, the engineering lags design. So by the time engineering gets back to the designers with the data, the design has already progressed. So all these could be avoided by adapting the solution connecting CATIA and Simulia on 3D Experience platform. I think, should we go on to the next one, Jessica? So let's see what are the product development challenges. As I mentioned earlier, always typically engineering lacks design. And so how do we feedback or impact the design in a way that we design the best product possible? As you can see in this video, there's a multiple variations of the heat exchanger. So there's no way in a traditional way or test-based method that design can catch up getting the feedback from engineering. Only way we can do is with a digital process. And compressed vehicles cycles, as mentioned. So getting these heat exchangers from a supplier, and they will only have a limited number of heat exchangers. So it's not possible to evaluate all the possible options and pick the best. And also, it's difficult to have an integrated evaluation of all these combinations. And also, if you look at this vehicle, there's thermal issues, structural issues, aerodynamic issues. So all these competing objectives needs to be balanced to bring out the best vehicle possible. And typically in a vehicle OEM, you have departments, they are not connected. So the information flow is very much limited. And also on top of that, we also have budget and time constraints. So these are the challenges the vehicle manufacturers face. And now let's see how we can address these. So how can 3DS address these challenges or help address the challenges? With 3D Experience platform, we have a single source of truth. So one model can be shared across different disciplines on 3D Experience platform. And we can start the digital evaluation from day one, from concept stage. And we can integrate a design at any stage. You don't have to rely on the supplier or delivery of things or subsystems. You can, once you have a CAD model, you can drop it in a vehicle and evaluate it at any stage. And you can share the data across different disciplines so that you can realize the best possible balance between competing objectives. As we are doing everything digitally, there's significant reduction in prototypes. And also, we have very good collaboration between modeling and simulation. So you can see in this animation how the decisions can be made and discussed, and at the end, do everything we do on in a test facility can be done digitally to realize the best possible design. And also the information you glean out of these studies are unmatched. There's no way a traditional method can offer these offer whatever we get out of a simulation. What are the unique capabilities of our offering? The offering we have, it has been adapted by many clients across the world, and it has been validated and published in numerous conferences and in papers. And this has been proven over and over again. And it's also significantly reduced time and cost. And we have best practices to eliminate methodology development. So once our clients adapt our solution, and they have the best practices that have been developed based on the experience we have we have gathered over the years. So they don't have to develop a methodology to address the engineering problem. We have it available, so they can go and hit the ground from day one to engage in a development process. The solution can be used right off the bat. And we can do multidisciplinary evaluation on the single platform. As you can see in this image, we are looking at thermal performance, aero performance, and also we also can see how heavy the part is. So all these can be realized with our offering on the 3D Experience platform. More than anything else, fast and accurate, robust solutions. And the solution doesn't depend on external factors that can delay or derail your release schedule. So we have a solution that will converge and is accurate, and we can even do certification based on our results, and it's fast to meet your design phases based on. In some cases, you need a solution that is just a trend prediction. So we have a solution for that, and when the design moves along, you can have a very accurate solution that can also help to certify the design.
Yeah, thanks for the introductions. And here we want to present a use case, which is the cabin comfort and HVAC system, and want to demonstrate the powerful tool that we can use to analyze the cabin comfort and HVAC and thermal systems to provide a superior user experience and product to the customers. In terms of cabin comfort design, the goal is to provide a delightful customer comfort experience while maintaining high efficient vehicle. And it is more important for the next generation vehicle, which means the hybrid electric vehicle, the electric vehicles, hydrogen electric vehicles, and autonomous driving vehicles. And it's more important because we need an efficient cabin and thermal system to relieve the range anxiety. We need to provide the sufficient energy to cool or heat the cabin and the occupants, and also to properly manage the thermal inside all these electric machines and batteries and so on and so forth, so that we can relieve the range anxiety from the customer. At the same time, comfort is another focus for the autonomous driving vehicles, because the driver and the passenger will pay more attention on their immediate surrounding, the cabin, than on the road. So it's more essential to provide a delightful cabin experience. At the same time, there are more and more technology being integrated inside the cabin. So we need to make sure that we design the cabin that with high quality and robustness when we integrate all this technology together to form a customer's experience. And we believe we have the right set of tool to accomplish this goal. And one of the most important tool we have is Daimola behavior modeling tool. And Victor will going to introduce how we can accomplish a better design with the Daimola system tool. Okay, so I'm handing over to Victor.
Thank you, Chinwei. So first of all, I'm going to introduce what is Modelica and Daimola technology. So Modelica is a special purpose programming language which is object-oriented and which has the main aim to be able to model cyber-physical systems, mixing multiple domains like thermal, electrical, mechanical domains. So we most of the time pick equipment from a library, drag and drop into a diagram these equipment, set them up as parameters like inertia, like mass flow rate, and so forth and so on. And we assembled the entire system level model, and thanks to our Daimola technology, which is the kernel to transform a Modelica model to a simulation model, we apply automatically advanced applied mathematics, advanced numerical techniques, and time domain solver to be able to reach our goal, which is to have time domain curve for all the parameters we have entered into the system model. This is equation based, so this is very efficient because we can easily reuse models that has been designed for sizing heat exchanger or sizing electric drives. So we can also highly efficiently solve cyber physical systems. So on top of the Modelica capabilities, we also use functional mockup interface (FMI) capabilities with Daimler. And how we use it is like when we have a Modelica model, we are able to manipulate the equations of the system to match a predefined set of inputs outputs for the model, pack this into what we call an FMU, functional mockup unit, thanks to the FMI standard. And this FMU can be re-imported into other tools in order to co-simulate, or just also for model exchange, to be able to execute the model and solve all the equations and the variables along time. So when we talk about sustainable electrical vehicle or sustainable vehicle, we talk about being able to assess all the vehicle missions and all the services that the vehicle brings to the customer. So every different type of driving modes or charging modes or parking modes. So and we take these missions and these services, and we want to evaluate, for example, the range, for example, the aging level of the battery, for example, the time to charge, for example, the passenger comfort and drivability at the same time, and balance all these target attributes with a system level model that we see in the middle, combining, for example, here a heat pump model made in Modelica, and also an electric drive, a battery pack, and a vehicle dynamics model made in Modelica language. So here is the example of the electric powertrain model combined to the chassis model. What we see is that we reuse a lot of existing models from libraries. And these models are fully customizable because they are written in Modelica language. And from this model, we have the driving cycles, the driver, the chassis, the driveline, the battery pack with its aging behavior, so the vehicle thermal management part. And what we can do with this type of model is that we can really balance efficiently the energy and thermal behavior with the vehicle performance, like the 0 to 100 kilometers per hour performance, so the drivability performance, the jerk evaluation, and so forth. We can also, of course, predict aging and range for given drive cycles. And we can really do architecture trade-offs thanks to the very low CPU time of these models, as well as control design. Regarding the thermal management aspect, so the battery pack, the electrical drive is going to be cooled down by a heat pump, and this heat pump is composed of existing equipment and that are assembled to have a air loop, a glycol loop, a heat pump loop with phase changes, a simplified cabin model, and a couple of heat loads. So that is a very interesting model, because we can definitely size all the heat exchangers, all the pumps, all the fans that we have in this model. We can accurately predict the vehicle overall thermal behavior. We can, of course, study architecture trade-offs and control design. And for example, you can tracing along an entire cycle the coefficient of performance for an extra hot day or a standard day, as you can see on the right. Here is a typical example of the CO2 heat pump model, where you see we have modeled all the different heat exchanger for cooling and heating up the cabin. And you can see on the top the pH diagram that you have during the driving cycles of an extra hot day. To sum up the key benefits and the values, we have an entire vehicle model that couples a heat pump and a very complex thermofluidic circuit together with an e-drive and a vehicle dynamics model. And the coupling of two is flexible and open, because we use Modelica language. This is highly flexible, and we are able to have the two open standard, Modelica and FMI, inside this model. We have very high fidelity models, and we use compelling libraries that are bulletproof, I would say. We have a model that is very efficient in terms of CPU time, and then it's tied up for massive simulation and massive trade-offs. And we are reusing the community knowledge and the partners' knowledge in all these libraries. This means that you can extend and replaces your physical test very easily with this type of model, replacing all the outliner condition that you don't want to do in a test rig or in a vehicle. You can manage your IP and your engineering know-how, because the models are open. So all the modification you do on the models, they are consolidating in your libraries, in your own models. We cut down the time to market, because we are able to select with this type of model, so the best workable solution. And we easily break the silos, because the system architects can reuse this type of model. The control engineers can reuse this type of model to optimize the control of the heat pump and of course, of the electrical drive train. And the thermal engineers that can understand the effect of the thermal sizing and the different heat balance between the different components, thanks to the multi-domain models. Up to you, Chinwei, for the rest of the 3D, 1D.
Yeah, thanks, Victor. And thanks for a nice introduction on the 1D system model for a system. In the 3D analysis workflow, we adapt a powerful suite for CFD and thermal analysis. And for cabin, shown here right now is the defrosting workflow. We're able to predict the defrosting of the windshield and the windows so that we can provide proper visibility for the driver in the winter days. We're able to predict the defrosting patterns, the speed to defrost, and help the designers to design the defrosting and heater flow to optimize the defrosting efficiency and speed. And after we finish the defrosting, we move to the next workflow, which is the cabin comfort workflow. We're able to simulate the heaters, the heating vents, the foot duct, the face duct, and how the airflow help the human body to heat up and keep in comfortable temperature range. We're able to simulate different body type, different clothing options, different gender, and their perception of the temperature and the comfort level. We're able to calculate their thermal comfort during the heat up scenario and see how fast we can reach a comfortable cabin environment in certain cabin design. And shown here is a case study that we compare different 3D design, different insulation materials, and how that impact the cabin heat up and impact the human comfort. We're able to predict the heat up speed, and because of the different material impacting the human comfort and impacting the thermal losses to the environment, and how fast you can reach the level of comfort that desired. Okay. So this is just one of the example. We can use a 3D workflow. We can also use a 3D workflow to analyze like how we can use local heating to more efficiently heat the human body instead of heating the whole cabin, to provide a comfortable but also efficient human comfort design. So what we can do is including the thermal comfort of the occupant, the seat comfort for designing the different seat, and the local heating or cooling on the seat, and acoustic comfort that the occupant perceive from the HVAC systems, and also the interconnectivities in the whole cabin technology design. And we choose Simonia PowerFlow suite to do the analysis because it deployed the lattice Boltzmann method-based software, which is high accurate and can turn around faster comparing to its competitors, and it can be easily parallelized and to accelerate the simulation if needed. And we provide a equivalent to a physical prototype, and you're able to verify all this thermal and flow design in digital world without ever building the physical prototype. So we can accomplish a lot with a 3D design model and 1D design model, but there's something beyond just 3D or 1D design. That is when we need to integrate the system, we need to integrate the 3D cabin with the 1D thermal system together. And that is essential because we need to tune how the different part of the system work together. And we need to trade off between efficiency, comfort, and durability in the whole design. You need to do that with the integrated system so you know what you're trading off. And also we want to drive in the different real world conditions. Some conditions need to be brought into the 3D model, like the different solar load, how that impact the localized thermal aspect from perception from the occupant, and need to be verified only with 3D analysis. But part of the real world driving can only be verified with a 1D system. So that's why we need to integrate them all together to do the final design verification. So the benefit of bringing the different 1D and 3D system together is we're enabled to improve the accuracy because we capture the overall behavior and the system interactions. So we go beyond just silo system and can improve the accuracy. Also, we provide a trade-off between different aspects, noise, defrosting, and heating or cooling, and with the interaction of different systems. We're able to provide a better cabin and thermal system because we understand everything that is important in the whole system. So we can do the optimization beyond just a waterfall design paradigm. We can do the optimization with everything considered. And then finally, we can save time and cost on physical prototype because the whole system integrated is equivalent to a real vehicle prototype. So we can save time and cost. And the goal is the first prototype you generated is the last prototype, and just to verify the digital design is correct. And that should be good enough. How to do that? In the cabin comfort and thermal system example, we bring the silos together by co-simulations. On the 1D system model, we take the output from the 3D model, that is the cabin return air properties, the temperature, humidities, and pressure. And also we take the sensor value from the cabin and ambient sensor inside the 3D model. And then we simulate in the system model. And then we output the AC air property and defroster air property back to the 3D model. So in the 3D model, it's the same thing, but just different way. The opposite way, we take the output from 1D model and feed the measurement back to the 1D model. So these two models will run in co-simulation scenario. That means they're running in the same drive cycle together while exchanging the information during the drive cycle. We are able to accomplish this easily with FMI. So FMI stands for Functional Markup Interface. It is an industry standard for model interface in automotive analysis and beyond. It allows us to integrate the model easily because it's an industry standard, and it allows us to share the model through organizations that are using different analysis tool or from different vendors. The benefit of that is that you can use FMI in almost all the commercial available tools, and it's ready for periodizations. It allows you to include embedded system and controls in various of analysis. And also you're able to use FMI to black box your model and exchange between the OEM and suppliers while you keep your IP, but then you can exchange the model behavior between organizations. And we use the FMI tool and with Dymola and PowerFlow to accomplish this case study is to size the HVAC system with energy efficient cabin. So the driving scenario is on an extreme hot day in Arizona, Phoenix, Arizona. The temperature outside ranged from 25 earlier in the morning and 37 later the day. And that will be a very hot environment. It's in the desert. So we want to simulate the vehicle driving cycle during this hot day environment. So the vehicle drives through WTC drive cycles, and we're able to estimate the cool down time. So when the vehicle starts in the hot day, it will be very hot. So we turn on the AC, try to cool down the vehicle. So that's the first KPI is the cool down time. The second KPI is the cooling power that consumed by the HVAC system. And then we try to compare is two different design. One is the design with the normal glass roof. The second design is the vehicle with the insulated frame, so no glass roof, but insulated roof. So with the integrated thermal system, we're able to simulate the interaction between the hot cabin and the HVAC system, and how that different insulation design on the roof impact your HVAC system energy consumption. So through this case study, we understand we are able to reduce the time to cool from 13 minutes to 8.5 minutes. And also we reduce the energy consumption by from 3.26 kilowatt to 3.06 kilowatt, 6% reduction in the energy consumption. So we're able to simulate all this similar scenario that study the interaction between 3D design and 1D system model by the 1D and 3D integrated solution. We're able to do sizing so that you will not over design your HVAC system, but you can still keep a high quality occupant comfort with that more efficient HVAC system design. Okay, so again, let me quickly summarize the benefit of integrated system. We're able to improve the cabin comfort through digital calibration. We're able to understand how the system interact together, so we know how to tune the systems and make them perform properly. We're able to satisfy customer experience in all conditions because we already consider everything that is moving in the cabin and thermal system. We're able to reduce the issue and delay because we already simulate the integrated scenario very early in the simulation scenario. You don't need to wait until you have a prototype and test drive and find an issue. We are able to identify those issues early on with the integrated analysis. And with Dassault system, we're able to perform such integrated analysis very easily because we have the best in the class 3D cabin comfort analysis workflows. We have the class-leading cyber physical system model, and we have a panel of experts that we have a lot of experience in those integrated workflows. And also we have a mature professional partner community and networks that can provide all the libraries or all the different systems that you need for designing the whole vehicle together. Okay. So this summarizes this case study, and I'm going to hand over to Victor.
Thank you, Chinwei. So now it's a good transition to the fact that we want to introduce here two key partners of Dassault System. The first key partner is Alex Piccarelli from the Claytex company, and the second one is Manuel Graber from TLK Energy company. And I will let them introduce themselves and let's say discuss about what their customer valued the most when they are having services together with them.
My name is Alessandro Piccarelli, and I am an engineering director at Claytex, a Dassault System solutions partner. At Claytex, I oversee the development of Modelica libraries and the delivery of customer projects that utilize Daimler and Modelica. The tools we use are built on open standards and also provide access to the model equations, which is extremely attractive to our customers because model customization or indeed model development can also happen in-house at the customer site. This means that engineers do not have to depend on the software suppliers to implement any specialized components that they might need. They can do this themselves and keep the IP in-house. Daimler is available in both standalone and platform integrated versions. Within the 3D Experience platform, we can couple our systems models to CAD, FEA, CFD, and parameterize our models from a single source of truth. We can also automate tests linked to project requirements to make sure we are still on the right track at any point along our journey. The code our MBSE software generates is automatically optimized every time we compile the system models, enabling low CPU solve times and high numerical efficiency. This allows us to run, for example, full vehicle models including their thermal management systems and driver-in-the-loop simulators, but do not require tabularization of the complex physical behavior of the components to achieve a real-time performance. This ultimately gives the drivers and engineers an extremely realistic virtual vehicle to use for vehicle development, setup, and testing. The scalability of the models through plug-and-play approaches that are the basis of our application libraries enables their use from desktop workstations to hardware-in-the-loop simulators and driving simulators. Claytex specializes in systems modeling and simulation, and we have been working with Daimler and Modelica for over 20 years. Today we distribute products from Dassault System, develop Modelica application libraries and related tools, as well as provide consultancy services and training courses on all of this. The Modelica libraries we develop have already been optimized for performance and numerical robustness, and are built on top of a consistent model architecture. The user can then concentrate on the application of these models to analyze their integrated systems and optimize the overall design and control strategies. They can do this prior to any physical prototype existing. We integrate other Dassault System partner libraries within our vehicle model architectures to enable a fully integrated systems approach to vehicle modeling. Customers can take advantage of our extensive range of training programs to get them up to speed with the tools in the quickest and most effective way possible, focusing specifically on their area of interest. Through our consulting services, we help clients apply the tools in many different ways. For example, we have recently helped a major automotive OEM virtualize several of their durability test procedures. These test procedures involve hundreds of tests that are repeated a large number of times in the real world to quantify the performance and robustness of a new design. Using the virtual durability tests that we set up for the OEM, it is now possible to simulate overnight what it would otherwise take months to do in the real world, enabling many more design variations to be considered and saving hundreds of thousands of pounds. As the level of automation increases within automotive products, we are continuing to evolve our product offering to support the testing of features such as ADAS and fully autonomous vehicles. We are integrating all of the vehicle physics models developed in Daimler Modelica with sensor models and simulating the complete system in a virtual world that enables our customers to understand the interaction between the sensors, the vehicle physics, and the dynamic world around them.
Thank you, Alex. Now I'm going to introduce you, Manuel Graber. Hello, Manuel. Can
Hi.
you please introduce yourself and what you're doing with Dassault System?
Yes, of course. Hello, my name is Manuel Greber from TK Energy, Germany, Aachen. I'm CEO here, but I'm also a technical expert, so I have many years of experience with system simulation and, of course, the Dassault products. We mainly use Daimler. And let's say the main reasons why we use Daimler in many projects are 3 points. First of all is the equation-based modeling language. Victor already talked a lot about it. That's really one key point, what we need for our daily work. Second point is the openness. I will say some more about it in the next thing. And the third point is the really highly efficient algorithm. So as well the numerical solvers and also the symbolical pre-processing of the equations is very good, and this just helps us in our daily work. Some more details about these points. First, about the modeling language. We are mainly engineers. So we have a background in thermodynamics or process engineering. So we're not computer scientists. Of course, we use computers for simulations, but we don't, we are not expert programmers. So we really like this equation-based modeling language because it's about writing equations and not programming code. And that's much closer to the way we think about our problems and what we just fits to our approach, writing equations and thinking about equations and not about code. And Modelica as this high-level modeling language is really perfect for us for these topics. And I think, that's really the one of the big benefits of Daimler. But still, it sounds very easy just writing equations, but still it's a very powerful language. So you also have the object orientation and a different concept there, which enables us to build really reusable model libraries. So it's also a very good way of reusing models and knowledge across different projects and just getting better and better. The second point I said is the openness. Let's say this openness, I mean, of course, one side using Modelica as standard language is open because this enables us to reuse the complete ecosystem of Modelica. So there are a lot of free libraries available and, of course, commercial ones. Usually we more stick to the commercial ones. But there are many different use cases, and sticking to Modelica just enables us and other users to gain much benefit of it. And the other way of openness, I mean more the export side. I want to mention the functional mockup interface, which is also a standardized interface to export models from Daimler in an, let's say, executable form. So it's more the black box form, but it's still a very nice way of exchanging models between different tools. And this enables us, for example, to use models we develop in Daimler in other many other applications, including third-party tools. We use it, for example, for optimization. We use it for hardware in a loop tests to export the models to some real-time targets. And there are many other applications possible using this interface. And that's really also a very strong point. We can develop the models in Daimler and use the complete Dassault tool chain and all the tools Dassault provides on the platform. But of course, there are the world is large and there are other nice tools and stuff available, and this really helps us also to bring the models to the complete world. The third point I said is about the very good algorithms in Damola. And that's really about the symbolic pre-processing of the models. You can imagine they are very large equation systems. If you click it together, and in the end, Damola automatically transforms to a, let's say, to the core set of equations that are needed for the numerical solvers. And this works very reliable and good. And then in the end, the numerical solvers that are available are also very helpful, because we deal a lot with, let's say, a two-phase fluid flow, refrigeration cycles, for example. And these are very challenging because they are usually very coupled systems. They are nonlinear, very nonlinear, and stiff. And that's altogether very challenging for differential equation solvers. And Damola includes state-of-the-art variable step size solvers, and they are tuned very well. And in most cases, we get very good performance, low CPU time, and we can really simulate complicated systems. So to summarize the benefits, Damola and the Dassault tools deliver for us, it's enables us to solve challenging engineering tasks for our customers. And it's a very powerful tool to understand and improve dynamic systems in general. So talking about Damola. So to also provide some words about what we provide for customers in the context of the Dassault products, and especially Damola. The first important thing is probably our library. With our partner company, TK Thermo, we develop a library. It's called Thermal Systems, and you can also, you have seen some screenshots before in Victor's slide. So it's also sold by Dassault directly. You can buy directly with Damola. So we developed this library for many years, and we use it in own projects. And I think there's a lot of trust in it and expertise, and you get ready-to-use component models for thermal systems, especially two-phase cycles, but also one-phase, water cycles for battery cooling, heat pumps, air conditioning. There are many different applications with this library. So customers can directly buy this library and use it. But on top of that, we also provide services and support, because it's a changing topic and you still need experience. And I think the most successful customers are doing both. They are using the library, building up models themselves, but they also work together with us, and we help them to speed up real quick, because we build models for them, specialized customized models, but we also help them to learn the language Modelica and to use the libraries, and also to solve problems. And of course, we also support just if there's too much to do, we just help them out with their daily work. On top of that, we also provide, and that's quite unique, I would say, we also provide testing and measurements capability. So we also have own labs available, and we do measurements, for example, compressor test stands for refrigeration cycles, different automotive components, systems to some extent, and we provide these measurements, we build the test stands, we design experiments, and usually that's also combined in a modeling and simulation project. So we can really deliver both measurements and simulation. And I think that's really helpful, especially for this thermal domain, because here it's still important to back up each simulation, at least with some measurements. And of course, lab time is expensive, and simulation can dramatically reduce it, can really help you to save a lot of time and money by reducing the number of experiments. But in the end, I believe this number will never completely go to zero. So at least in the thermal domain, you always need some measurements to back it up. yes, that's basically all I have to say for introduction.
Thank you, Manuel. Now I propose to have you, Alex, maybe Chinwei, for example, to have, and I will ask you at least 2 questions that we have in mind. The first one would be for Alex. And maybe you can complement, of course, Manuel. There's no issues, and Chinwei as well. We often have a question from automakers or from supplier of electrical powertrains, how to derive an optimal control strategy of a battery electrical vehicle, or I would say hybrid electrical vehicle, to maximize the range. Could you please elaborate, Alex, how you could help with that, and also Emmanuel, how you could help? So and also maybe elaborate a bit also around what is the split between 1D and 3D simulation that would be appropriate for doing this type of analysis.
Okay, yeah, sure. So in the projects that we've been involved in, the approach has always been to start off, and they have been new electric vehicles. So we're starting from a blank sheet of paper here. So fewer constraints. The approach has been to take out any limitations by not using existing heat exchangers that are available on the market, by not constraining ourselves to pre-existing components. So going in there and saying, okay, what are our objectives? By how much do we want to increase the range we're predicting we might get, or the current electric vehicle has, and what are our objectives? And therefore, start off with models that are not constrained, so that we can dial in what the objectives are and understand what amount of heat exchange we need, for example, in the heat pump heat exchangers, how much heat would we need to, for example, draw out of components like electric motors to then redistribute to the cabin and the battery in cold climates where we need to bring these up to working or habitable temperatures as quickly as possible. Once we've run through several control strategies, deciding whether we want to include a phase change material thermal battery in the system, for example, that we can pre-charge and then use that thermal energy, distributing it to the battery and the cabin on a warm-up. Once we've gone through 7 or 8 of these control strategies which we want to investigate, we then typically choose the highest performing ones in terms of increase of range or decrease of energy that's used for the thermal management, and take these and start to find out, okay, what are our constraints with styling, for example, packaging, and then starting to bring in components which suppliers could make, so that might not exist, but could make, and start to dial in the compromises to figure out, okay, in the real world, what would we expect to see in terms of vehicle range or improvement of energy consumption of one control strategy versus the other. And we're slowly bringing in things like gear drive losses, for example, losses in the electric motors if we were to chill them to use that heat elsewhere in the vehicle, and bringing in all these physical limitations that would exist in the actual vehicle. But if we bring those constraints in right at the beginning, we're kind of limiting what is possible, and in a research environment that is very limiting, and you don't want that at the start of the analysis. So we do need this integrated system, which is your vehicle, bringing in all of these subsystems and understanding how they work with one another to find what the optimal design is. If you don't consider them all, then your end design, you're going to have problems with it. You're going to find out, oh, I didn't consider this, I didn't consider that. And I'm not saying you've got to start again, but thereabouts. So that's the approach we've taken with several OEMs now, and utilizing the libraries that we've seen and talked about. And we've been successful. Also cutting down on physical testing, which costs loads of money and time and involvement of people. So that's been our experience at Claytex. So I'll let
impressive. Next, Manuel, do you want to add something?
Maybe can add something you also said about the 3D 1D topic, because I think Alex said that's completely true. So the simulation really helps us to go one step back and really start on a blank piece of paper and just see what's possible, and then you can improve it step by step. And for the first iteration, you don't need really 100% accurate models. It's just if you design a new vehicle and you go one step back and think about what subsystems make sense, what configuration makes sense, you don't need the complete accuracy of models. It's just you need to get the physics right and the principle stuff, and you understand it. And then if one variant is much better than the others, then you can pick it. And if they're close together, of course, you have to increase accuracy and look closer. And then in the first part, by now, I think it's you can completely do it with 1D. You don't need all the details of 3D models if you're in this concepting thing. But then at one stage, it might be important. Then how is the in our case, it's often the use case. If you look at heat exchangers, of course, the airflow is usually limiting the heat transfer, and then it's very important how the airflow and the heat transfer is really resulting in the vehicle, and that's something you cannot answer with 1D. In 1D models, we usually take heat transfer coefficients at given, and the airflow, of course, a little bit airflow pressure loss stuff you could also add there. But I think it's really helpful in this case to take 3D simulations, calculate the airflow distribution, mass flow distribution, calculate heat transfer coefficients, and then pass them automatically to the 1D simulation and reuse the results there. So that's a very typical use case we do a lot.
Yeah, and I also agree with Alexandro and Manuel. So it's very important to make sure you have a proper heat exchangers and not limited to the existing design. In our example, helping the OEMs providing a better design, they traditionally, they will just carry over the heat exchangers from the previous generation of vehicles and try to use that. And also, it tends to have a larger heat exchanger than needed because they're not sure about the airflow design, so they need to leave a lot of headroom. But that almost always tends to become over-designed, so that you have too much weight to a vehicle. So that gain weight, that means less fuel economy. Or you have too much air go to the heat exchangers, that means you have more drag because the air go to the heat exchanger that increase the drag to the vehicle. So what we try to help them is that we provide a concept design for a workflow for the 3D design on the cooling airflow, so that they're able to simulate the heat exchangers and the cooling package that include condenser and other heat exchangers. And in the 3D design way, they know what's the airflow, they know what's the real performance of the heat exchangers, not just on the test bench, but on the installed conditions. And we're able to predict what is really, what's the real performance of that heat exchangers. And then they don't need to over-design that much. They still want to leave some headroom, but they won't over-design that much. And they can increase a lot of efficiency of the vehicle. And furthermore, we also work with heat exchanger suppliers to provide a digital library of their heat exchangers that is feasible to manufacture. So we work together with Denso to provide a heat exchanger library that include billions of possible heat exchangers that bounded by the manufacturing constraint. And then the OEM can drop in those heat exchangers, and they can do optimization study with those billions of heat exchangers and able to find the best design and early on, so then they know what is the performance of those heat exchanger components. I think that would definitely help to provide more efficient vehicle, not just make assumption and leave a lot of room that can be improved on the efficiency side.
Thank you, Junwei. Manuel, how are you contributing to a better energy efficiency of industrial processes?
Yeah, so that's a little bit completely different topic, but it's also very, where we use the Dassault tools a lot, Daimler. It's really about industrial processes. So it's not now the car, it's more manufacturing the car. And we see, or we also believe that this interest in saving energy in, let's say in industrial plants, I guess it will increase in the next years a lot, because a lot of companies try to reduce CO2 consumption. And I also believe the same tools, 1D simulation with Daimler and also 3D simulation for some details, helps a lot in improving these systems, because the energy systems in these industrial plants are quite complex. We have different types of demands, heat demand at different temperatures. You have storages, production process, pressurized air, cooling cycles and all these things, and they all work together. It's quite complex. We have controls, and 1D simulation also helps a lot here to understand the complete system and try out different ideas how to improve the energy efficiency. So from this point of view, it's again similar to an electric vehicle. It's a system, and you have different energy flows and demands, and it's very complex, and you can use simulation to try out new ideas, and you don't have to, if for complete plans, it's even impossible to try something out. So, but it's, really in the basic, it's same ideas, and we use same tools, maybe a little bit different libraries, but the workflow is quite similar.
Thank you. And thank you everybody for joining. We hope you had a nice session.
In the past hour, we have listened to our experts talk about how different thermal systems can be designed using our 3D Experience platform. On 3D Experience platform, we can bring modeling and simulation together to realize the best possible vehicle. On the left-hand side, what you see is the designing of a vehicle. You can see you see the body in white, and also the components and the subsystems that generate heat. On the right-hand side, the engineering work is being done on this vehicle for the same subsystems, and we are running a simulation to ensure that vehicle is designed to meet all the driving conditions. So we are sweeping through different driving conditions of this vehicle that will be subjected to, and make sure that this meets all the engineering KPIs. This is only possible using a digital simulation or simulation-driven design. And the information you can get out of this cannot be matched by any other method. So the only way you can bring in modeling and simulation together in this and bring it in this ecosystem is through 3D Experience platform. If you look at a vehicle, there are so many subsystems that generate heat. I have shown some of these here, starting from engine cooling, electric motor cooling, battery cooling, fuel cell cooling, heat pump and HVAC, and power inverter cooling. All these can be brought together on 3D Experience platform to design the best possible vehicle. So we can it's not an understatement to say thermal system is the unsung hero of the vehicle. So you can realize the best possible vehicle by designing it on the 3D Experience platform. You can get more information about CATIA and Simulia and the latest developments and access to our expert in the following websites. And if you have further interest and if you want immediate access to a person to talk about how you can go to the next steps, you can contact our sales at the website given here. And whether you're a professional or a student, you can get up to speed and design the best possible thermal system. And we have all the resources in our learning center to enable you, to make that possible.
I will have a final word on open standards. So we have discussed about Modelica language and FMI, and here you find the website about Modelica Association and FMI standard here. And the last but not the least, you can find here our partners that have played with us during this the past hour, which are Claytex here and TLK Energy. Don't forget to flash the QR code that you see on your right to get more information. Thank you very much.